Okay, let me start determinants. This is Calc 4, Lecture 10. I'm not sure if I can finish this in one session, so maybe two. And first notation, given a square matrix, so determinants are defined for square matrices, and if A n by n is square, in fact it's n by n, we denote determinant of A as like this either or like absolute value. Both of them are used. Now, we can define determinants in many ways. One of them is using like induction, so inductively define it. It means that we define it for, say, a 2 by 2 matrix, then we define it for 3 by 3, then 4 by 4, and so on. But in fact, what we do is define it for 2 by 2, then define it for n by n, say. And then we say, okay, now n can be 3, 4, 5, blah, blah, blah. So it is defined for any other the matrix, square matrix. So for a 2 by 2 matrix like this, it is this times this, as you see, the diagonal, minus this times this. Okay, so it is the main diagonal minus this diagonal. So the product of this, if I call it main diagonal, minus the product of this, which is the other diagonal. And so, for example, determinant of, say, well, let's just write this simple. 2, 3, and 4 is 1 times 4 minus 2 times 3. So, which is 4 minus 6, which is minus 2. Well, it's good that it is negative. So, if you see that this is, in fact, this is not absolute value. This is some notation. So, determinant is a number assigned to a square matrix. And you will see how, but the applications, for example, the Cranius rule, for example, and in other places. But determinants are important, and we will see why when we do some problems. So we have defined this for a 2 by 2 matrix. So let's say if before defining it for an n by n matrix, I need some more definitions. So let me erase this thing. And I would write it from the book, write the statement in the book is amazingly good. So I cannot put it in any other format. But it's so nicely written. So the definition, in fact, is that given A n by n, which means it is square matrix, then the minor of entry Aij, so minor of entry Aij, denoted by Mij, is the determinant of the submatrix that remains after the ith row and the jth column are deleted from A. The cofactor Cij is, well, we use cofactor. In fact, Cij is minus 1 to power I plus j mij. Okay. Let me see if you can see that. So this is I plus j here. I plus j, aij, mij, and this is cij. So, well, let me give you an example of this thing. Yeah. So, well, let me write a 4x4 matrix. A11, 12, 13, 14, A21. So, M11, delete. So you have to delete, either write it down on a sketch paper and delete that, or just do it in your mind. So delete that is determinant of this. This remains, right? A22, A23, A24, A32, A34, and A42, 43, 44. Okay? So M11 is this. Well, let's find M, and this gives me C11 is negative 1 to power 1 plus 1, M11. This is 2, so it is equal to M11. Okay? So C11, the cofactor, is in this case equal to M11. So let me erase this and write M12. And I guess that if I write M12, you get the idea. M12 will be determinant of this goes and this one goes. So I have A21 jump, A23, A24, A31 jump, A33, A34, A41, A43, A44. And the cofactor will be Cij is negative 1 to power 1 plus 2, and well, that's 1, 2. 1, 2. C12, M12. This is 3. Negative 1 to power 3 is negative, so that's negative M12. Negative M12. So the cofactor is sometimes Mij and sometimes negative Mij. So by now using this, well, let me give. We should do that. So let me write down the definition. So determinant definition This is the cofactor expansion given a n by n. Determinant of a is, we can use any row. That's interesting. Determinant of a will be sigma. So let's use row I. So I say ai j, and j goes from 1 to n. Cofactor ij. That's it. That is determinant. So this is called cofactor expansion. It's interesting that you can prove, I'm not going to prove that, but you can prove that this doesn't depend on which row I'm using. I can also use a column. So this is using a row. Using row I. Now I can use a column here. So a, I, j, in this case I goes from 1 to n, Cij. Then this is cofactor expansion. Using column j. So the column is fixed in this case, and so depending on the situation, if you are finding determinant by hand, then look at rows and columns. If you see a row or a column has like too many zeros, for example, because 0 times Cij is 0. So that makes things much easier for you when some of them are 0. Depending on the situation, you can choose one of them. But let me give you an example of 3 by 3 and the cofactor expansion. Most often you start with the first row, just by the knowledge. You are used to doing that. So, example, let's say A is 1, 2, 3, negative 3 to 5, 6, say 2, negative 8, say 12, something like that. So, determinant of A using first row. Okay? So it is 1 times determinant of, well, let me say 10, because then you don't get confused. So 5, 6, minus 8, 12. Right? So this is in fact Cij. Why is it C11? This is C11. And this is A11. And C11 is positive, because negative 1 to power 1 plus 1 is, in fact, this determinant is both C11 and M11. M11 and C11 are the same. The second one. The second one is C12. C12 is negative N12. So I will get negative 2 times determinant of, get rid of this and this, I will get minus 3, 6, 2, and 12. The third one is plus again. So C13 equals M13. So 3 times determinant of, get rid of everything except that. So that is determinant of this matrix. And we know how to find determinants of 2 by 2. So let's find it. So this equals 10 times 5 times 12 is 60, right? 5 times 12 is 60. Minus this, minus is plus 48. Minus 2 times minus 36 minus 12 plus 3 times 24 minus 10. Okay, so this is 108, is it? Yeah, 108 times that is 1080. This one is 36 and 12 is 48. 48 times 2 is 96 plus 96. And this one is 14 times 3. 14 times 3, 2, okay? So that is determinant. Now, I'm not going to add them. You can add them yourself. And now, let's add them because I want to find it using this, for example, and show you how they are the same. So this and this will give me 7, 6 plus 42. That is 8, 1, 2, 1, 2, 1, 8. I guess let's say 1, 2, 1, 8. Let's see, maybe I have made a mistake. So let's check. So let's check using first, using second column, right? Second column. Now, if I use second column, this thing. This thing. So I have 2 times something. 2 times C, that is 1, 2. Then I have plus 5. C, this is 2, 2 minus 8. C, 3, 2, right? So that is using this column. Now, what is each one? 2. Well, I can, in order to see which one is positive, which one is negative, I can do this. I can draw another matrix here. So this one will be positive, negative, positive, negative, positive, negative, positive, negative, positive, okay? So these are the signs. So this one will be negative, so it is negative 2 times determinant of, we get rid of this and this, minus 3, 6, 2, 12. And this is positive plus 5 times this, and they remain 10, 3, 2, 12. Let me double check 10, 3, 2, 12. Right. Then this one is negative, minus 8. Times get rid of this and this, I have 10, 3, minus 3, 6. Okay? So if you draw this picture, you will see which one has a positive sign, which one has negative sign. The rest is simply just write that entry times its minor, in fact. So, okay, let's see. This is minus 2 times minus 36 and minus 12. This one is 5 times 120 minus 6. This is 8 times 60 plus 9. Okay, so this one is 48, that's 96. So let me write it somewhere. So I have a 96 here. This one is 114, is it 114 times 5? That is, what's that, 114 times 5? Is it 560? 570. So 570, I guess. The last one is 69 times 8. Oh, gee. So 560 minus 8, that is 552, I guess, right? Well, let's see. Yeah, that's correct. So this is 1000. Let's put these together. That's 1000, and 70. That's 202. Is it? No. Did I make a mistake anywhere? Because it doesn't seem to be 9, 12, 18. Maybe it is, yeah. 9, 6. That is 8. Yeah, 12, 18. So listen. Okay, so as you see, I have the same thing. You can check this thing with other. In fact, what is happening is a determinant is, if this is a 3 by 3, determinant is the sum of all possible products of entries. All possible products of entries, products of 3 of them, say. If I have a 4 by 4 matrix that I did before. So, as you say, in this case, you see that there are just 3 of them are multiplied. Like this 5 is multiplied by this and this. This is an entry, so 3 of them are multiplied. And if I have 4 by 4, you will see that 4 of them are multiplied. So basically, it is a sum of, if that's 3 by 3, it is 3 products. I don't know what to call it. 3 products of all entries with certain, say, sign. So the sign depends on which ones are multiplied. So anyway, that is, I will stop now and